Hello, my name is Howard Cook. I'm one of the owners and the founder of Bay Area Retrofit, and I'm going to show you a method I developed to install shear transfer ties that are made out of lag bolts. For the first 10 years of this business, I did a lot of crawling under houses. I did a whole lot of construction, a lot of practical application, and I took my skills that I learned in graduate school to really study everything on the topic I possibly could, and develop methods of doing things that I thought would save time and money. And so I'm going to be showing you that right now. Well, the first thing I need you to understand is what a shear transfer tie is. So if you really want to get a good idea, please go to our website, and there's a video called Cripple Wall Retrofits. At minute 15, 30 seconds, you'll see a whole section on shear transfer ties. If you watch that first, this will make a little more sense. I will go over shear transfer ties briefly, and you may not need to do that, but anyway, you're not going to see much of me anymore. I'm going to go straight into the topic matter, and let me show you. When talking about earthquake forces, we refer to pounds of force. So let me explain how that works. What actually happens in an earthquake is the ground moves underneath the house like that. So the foundation and everything just goes like that. And then inertia wants to pull the house back like that and cause it to slide from its foundation. Now that is exactly the same as something pushing on the house. So let's assume that you have something that weighs, let's say it weighs 10,000 pounds, and it's pushing against the house, like this. That is the same as a ground acceleration measured in G's underneath the house. So we're actually looking at a ground acceleration under the house, and we're translating that into pounds of force that are attacking the house. So what it is, when we're looking at hardware and we look at anything else, we look at them in terms of pounds of resistance. So you're going to see references to different types of hardware, to houses being attacked by a certain amount of force, and that's what it means. So as we just saw, a ground acceleration underneath the house creates a certain number of pounds that are pushing against the house. So every piece of hardware, every linear feet of plywood, every single retrofit component provides a counterforce also rated in pounds. So we have a pushing force, that's rated in pounds, and then we have a counterforce that's also rated in pounds. So here, for example, there we have a half-inch bolt, and it can resist 1,340 pounds. In other words, that creates a counterforce in pounds against the pounds that are pushing against it. So we have force, and then we have counterforce, all rated in pounds. Over here we have another type of shear transfer tie. We're going to see some of those in a minute, and they can resist 925 pounds of earthquake force. And then this one right here is very important. This whole video is about lag bolts because they're such a special type of shear transfer tie, and I'm going to show you how it is that this 400 pounds per lag bolt was created, or why did we come up with this number right here. It's very, very special way that we came up with that number. And then over here, this is also resist earthquakes. This is a linear feet of plywood. So for example, if we have 4 feet of plywood, it can resist this much. Now notice there's pounds of resistance here, pounds of resistance here, pounds of resistance here. So every type of component that you find in a retrofit can resist a certain number of pounds of force. And you're going to see that referred to later on in this video. So this is a shear transfer tie. That's a piece of steel that corresponds to this piece of steel. Now this piece of steel is nailed into, this is called a floor joist. Now this is the floor you walk around on. This is the floor joist, and this piece of steel is nailed into here, into the floor joist, and it's also nailed into this upper top plate. So the nails come down like this. So the same thing over here. This is the floor joist. This is the floor joist. This is a shear transfer tie. This is a shear transfer tie. Here are the nails. So you see how the nails went into the floor joist right here. There's also nails that come down this way that go into the upper top plate, and right there is the upper top plate. So this whole assembly right here corresponds to this right here. What has happened here is the ceiling was torn out. This is ceiling. The ceiling was torn out in order to put these in because you have to get your hand in there somehow. Now, an alternate way, besides tearing out the ceiling, is to use something called a lag bolt. Now, here's the lag bolt, and what you do is you take this lag bolt and you drive it up through the top plate. So here's the upper top plate and the bottom top plate. You drive them up through like that, and you thereby connect the floor joist to the upper top plate. You basically do the exact same thing you're doing here. The floor joist to the upper top plate, the floor joist to the upper top plate. The lag bolt has come up this way, connects the floor joist to the upper top plate. So we've achieved what we want to achieve in that part of our retrofit. There are other parts that we need to look at, of course, the bolting and other framing, but that's pretty much it for the shear transfer tie. So if we do it that way, there's absolutely no reason we have to put a shear transfer tie here and here to connect the floor to the top plate, because we've come up here with the lag bolts, which has connected this, the top plates to the, the blocking and the floor right here. So what happens is earthquake force comes this way, pushes against the lag bolt, and then that lag bolt pushes against here, and then because there's the plywood there, it comes down here and it pushes against the bolt. So again, these are a substitution for the normal shear transfer tie. So we've achieved that. Now let me show you why this can be such a problem. This is a house where the ceiling was torn out to put shear transfer ties in. You can barely see one here, and you can see one here. And this was actually acoustic ceiling tile, so you can see the lines, and you can't even buy the stuff anymore. So in order for this ever to look right again, this owner is going to have to tear the whole ceiling out and put sheetrock up. And so what the contractor did to meet the building code is they put they put sheetrock right here, fire-resistant sheetrock right here, and they screwed it up according to the building code. Then they taped it, and then the owner had to, figure out what to do from there. So here's an example of the exact same thing. A strip of sheetrock was taken out right here. You can see the really rough, jagged edge that someone's going to have to straighten that out so that you can put a strip of sheetrock here, and the strip of sheetrock will go from here to here. Then you have to tape it right here, and then you have to somehow match this paint. So you have to go to a paint store and give them a section of the paint, then they have to match it, and they might get close. Usually they can't get very close at all. Home Depot will never get it close. So and then I just want to show you, these are the joists that we were talking about, and these are the studs, the walls. So the walls right here, the joists right here, and what could have been done here is some lag bolts could have been shot right up here along in these joist bays right in here, and we could have avoided the whole thing. Now, usually these ceilings have plaster or sheetrock on them, and in those cases, and it's usually 5/8 inch thick, it's not so bad. You can actually just put a strip of sheetrock here, and then you can tape it and more or less match the texture that's on the ceiling and get pretty close, and it's not so bad. But the real question is, why ever do that at all? I mean, if you can just use a lag bolt and go up here and up here and up here, say 10 times, take you 15 minutes, compared to tearing this out, patching it. When you tear it out of when it's plaster, you have to use steel diamond grinding wheels, makes a whole bunch of dust. It might be lead-based paint, silica if it's plaster, which is also quite dangerous. So I can only see a downside. I can't see an upside to doing this. So that's why I'm showing you this. But, a lot of contractors do this. They just take the strip out so they can get their hand in there, and it's a really good idea what they're doing, but it's not necessary, and that's what the real problem is here. So let me show you that again. This is such a simple concept, but it's good to repeat it over and over again so we get it. So this is the floor joist. The floor joist moves. It pushes against the lag bolt, which has been driven straight up. So the lag bolt is all the way through here. So when it comes this way, it pushes against the lag bolt. The lag bolt goes through the upper top plate, so the upper top plate is pushed this way as well. And this upper top plate is nailed with plywood down to where the bolt. So this upper top plate is equivalent to this, and see there's plywood right here. And so the plywood is nailed up here, and the plywood is nailed right here, so that when this this upper top plate moves this way, you know, the top of the plywood moves this way, the bottom of the plywood moves this way, and then it goes into the bolts right here. So this is an example of where we would use that. So this is a wall that, you know, the plaster has been removed from, and now rather than going up here and tearing out the ceiling and putting in metal shear transfer ties, we just use lag bolts. We just go straight up and down just like that. That's all we got to do. Do that maybe 10 times. You know, compare that to tearing out the, you know, part of the ceiling and patching it and buying, you know, match the paint and the texture and all that stuff. You know, what a difference. So again, these are the lag bolts that you actually see photographs. This is the photograph right here. So here's a lag bolt here, lag bolt here, lag bolt here. Right above here is the floor joist. So right above that is that. So there's the top plate, lower top plate, floor joist, top plate, lower top plate, and there would be a floor joist right there if you could see through the sheetrock. This is a construction detail. Now, a construction detail is something that it gives contractors and engineers a picture, a drawing of what they do. So here you can see the upper top plate, lower top plate. Here is the lag bolt that goes through it. And you see we've connected the floor joist to the upper top plate, which is what shear transfer ties do. That's all they're supposed to do. That's the function of a shear transfer tie in any retrofit. The sheetrock is still there. We haven't had to remove it. We put our plywood in. We nailed it up here. We nailed it down here, and we're all done. We have a complete retrofit right here. And the shear transfer ties was pretty simple. I mean, it actually simpler than putting in a conventional metal one where you have to drive in a bunch of nails. This is just you drive in one lag bolt with a power driver, and that's it. So now sometimes, it's fairly rare, sometimes we do, we'll drive our, we'll do a test. In fact, the way you find out if you have blocking up there or if you have a floor joist to drive, that's up above your top plate, is you take a drill bit, say maybe 6 inches, and you drive it up through the top plate. So you would drive it up this way, and you'd see if there's any framing. So you would drive it up after you went through about 4 inches, you would find that out. So here, let me show you. So here's the bottom top plate, upper top plate. This will normally be 2 inches. This will be 2 inches. Then you drive your drill bit, comes up this way, and if it hits wood, in other words, if you have sawdust, it's still coming out, that means that you have framing up here, and lag bolts will work great. If you don't find any framing up here, if it just punches right through, well, then you're going to have to do this. You can't get out of it. You're going to have to take this apart, put some blocking in there that's missing, and then put in your conventional shear transfer ties and all of that. So now that we have all these great ideas about how not to tear the ceiling out, we need to look at the lag screws, which are what this whole thing is based on. So we need to know how many to put in and what size they should be put in, and then also how they should be put in terms of what are the restrictions on their installation. So this is called an SDS screw, is what we actually use. It's made by a company, Simpson Strong Tie, and we're going to be looking at their tables, and they've done a lot of testing to make sure that these will work as we want them to. Now this is a table right here. This is from their catalog, and what it tells us is the allowable shear value. That shear value is basically saying how much earthquake force can it resist. Now the sole to rim connection, this is the sole plate right here, and this is a rim board right here, and that is the exact same thing. So this is the equivalent of a top plate, and this is the equivalent of the floor joist. And this screw right here joins the two together, just like you would see when you're doing a lag from the upper top plate to the floor joist. So what it's telling us here is that the connection between here and here can resist 250 pounds. Now that 250 pounds is actually much more than that. The 250 pounds must be multiplied times 1.6. And the way that works is, what it says is that if we were to apply 250 pounds of force against that SDS screw, it would not bend, nothing would happen to it. We could just push on it forever and ever and nothing would happen. Now, it also says if it's very, a sudden short-term force, it's called the low duration. If it's very short-term, it also won't have any problem. So if we increase that times 1.6 for a short period of time, it will also perform exactly as we want it to. So what that means is we can take that 250 pounds that we find in the catalog, which is for, basically the force of gravity, or how much force can be put on it for a long period of time. We multiply that times 1.6, and then we end up with 400 pounds per SDS screw. So what that's telling us is that our SDS screw, if it's installed correctly, can resist that amount of force. Now, the really critical thing to look at always are these footnotes. These footnotes, you can't quite tell how important they are just by looking at them. They're kind of small, but they are extremely important. So what this tells us here is that the minimum spacing of the screws is 3 inches. So we can put them at 3 inches apart, but no closer, in order for them to work properly. And the minimum edge distance can be is 5/8 of an inch. So it has to be 5/8 of an inch or more. Now the edge distance is this distance here. This is the top plate, or equivalent to the top plate. So the distance between here and the center of the screw can be 5/8 of an inch or more. Same here. Here's the edge of our joist. It can be 5/8 of an inch from here to the center of our screw or more. So that's what we're looking at there. So how do we figure out how many SDS screws we need? So here's an example of a shear wall that we built. It's 10 feet long, and we nailed it in such a way it can resist 8,700 pounds of earthquake force. And we have the 2 inches of penetration. So remember, we have to have that 2 inches of penetration right up here for it to be effective. And we have our 2 inches of penetration, and then we do our multiplier, our 1.6 earthquake multiplier, and we end up with 400 pounds of force per lag bolt. Now we have a 6-inch lag bolt. It will go 2 inches into the joist. Let me show you how that works. We have a 6-inch lag bolt. It's going to go through here. That's 2 inches. Go here. That's 2 inches. And this is the lower top plate and the upper top plate. And then it goes into the floor joist, another 2 inches. So we made our requirement of 2 inches. And so we divide that 8,700 by 400, and we get 21 SDS screws. That's what we need for our shear wall that can resist 8,700 pounds of force. Now I want to show you something about edge distances. That's always a problem. What it's telling us here is that the SDS screw, we want to get it right in the center of the joist. In new construction, the joists are 1.5 inches wide. That's the narrow face. Old construction, which was what we usually work with, is 2 inches. But in order to get the full value, our 400 pounds per foot, we can get 5/8 of an inch from this edge, or 5/8 of an inch at this edge in order to get it. If we can't get that, if we have to go less than that, let's say 1/2 inch or something, we have to use something called the reduction factor. So for example, if we can only get 1/2 inch rather than 5/8, we use a reduction factor. Reduction factor is a percentage that you multiply the value by in order to get a different value. So let's say we have a reduction factor of 66% when we get down to when we're at 1/2 inch. We multiply our 400 pounds by 264, 400 pounds by 0.66, and we get 264 pounds. So it's really critical to get right in the center of the joist. Get as close as possible. You want to be at hopefully right at 3/4, and then you'll get your full value for sure. Now over here where you have your 2 inch, this is the old growth ones where the joists are 2 inches wide. When we get in the center here, we get 1 inch, which is more than the required 5/8. So again, what we want is a 3/4. So because we've got that extra inch, we're actually getting an extra 1/4 of an inch of edge distance between here and here. And so these lag screws in 2-inch lumber, the old growth stuff, should probably be closer to 450. There's a bunch of fancy engineering calculations which I don't really feel like learning how to do, but that's a general rule of thumb. So how do we get them in the middle? That's the big question. I want to get these in the middle. So just imagine from a from a design point of view, from a just figuring out point of view, how are you going to do that? You got to get through here. This is the lower top plate, through the upper top plate, and then get right in the center of this joist. And if you look at it, well, you can put the screw in there, and you just hope you might get it. Might get it. You might not. It's pretty critical you get it right where it's supposed to be. So let me show you how that's done. This is something that's called a jig. And what that does is it keeps this drill bit exactly 1 inch away from the siding. I want to back up a little bit and show you how these two drawings match. So here's your siding right here, and then this is the siding here. This is the lower top plate. This is the lower top plate here. This is the upper top plate, and this is the upper top plate. And here's our floor joist, and here's our floor joist here. And this lag is right in the center. And the way we did that is we put our pilot hole exactly 1 inch from the siding. So here's the siding. Then we go 1 inch in, and we're going to be exactly where we want to be and go into the center of the joist. So let me show you a little bit more about the way that works. So here's the siding, here's the floor joist, and this is the hole that we put right in the middle. Now the way we've done this is we've taken that round steel stock that's got the hole in the center, and we've butted it up against the siding. Then we put this underneath the joist, and then we drilled up, and that put this hole right in the center of the joist. So for the 2 inch, we have a 2 inch piece of round stock, so with diameters 2 inches here. For if we have a newer 1.5 inch joist, this is actually 1.5 inches right here. But no matter which one we use, we will always get right in the center of the joist. So let me show you that one more time. So here's our round stock with the hole in it. That is equivalent to that. There's a drill bit that's going straight through this hole. Here's the drill bit coming right here. It's going into this floor joist right here, which is right here. So we've achieved this very, very well. We're right in the center, exactly where we want to be. So this concept is pretty hard for people to grasp and not going to understand without someone actually showing you the piece of metal and everything. So anyway, the way we have this jig set up is that this drill bit will be exactly 1 inch away from the siding. Now the siding is touching the outer face of the joist. So let me show you how this works. You see this, this is the lower top plate. The lower top plate, this edge right here is exactly in line with the outer edge of the joist. So this outer edge right here is the same as the outer edge of this upper top plate, and the outer edge of the upper top plate is right in line with the outer edge of the joist. So that means if we come in 1 inch here, we will have come in 1 inch from the outside face of this joist, so we'll be 1 inch there. And so what we do with this spacer, because this spacer keeps this hole, this center hole where the 1/4 inch hole is, it keeps it exactly 1 inch away from the siding, which is exactly, puts it 1 inch away from the this bottom plate edge right here, which is right in line with the outer edge of the floor joist. Again, we're 1 inch from the outer edge of the 2 inch floor joist, and that puts us right in the center. Now I really hate to beat a dead horse to death, but this is so important that I'm going to repeat it all over again. If you don't understand the practicality, understanding the theory will be absolutely no use at all. It end up being like an engineer. Sometimes we get engineer recommendation in a drawing and go, man, this guy absolutely has no idea actually practicality of things. So really want to make sure that the practicality is emphasized, and especially if you're an architect or an engineer and you talk to your contractor, you can say, hey, just make this round jig and put this center hole in it, and you'll be able to put in these lag bolts and save your customer a lot of money. So here we have a technician, and what he's doing is he's putting in a pilot hole with a drill bit. And that pilot hole is exactly 1 inch away from this edge right here. And the reason that's important is this edge of the lower top plate is exactly in line with the edge of the floor joist right here, which is 2 inches. So if you come in 1 inch from here, you will automatically be going in 1 inch from the outer edge of the floor joist. And if we go in 1 inch, we'll end up right in the center of the floor joist where we want to be. Now remember, to get full values for our SDS screws, we have edge distances to worry about. So the way the hardware is designed is you need to have a minimum of 5/8 of an inch. And if you have more than that, it will be stronger. So we have 5/8 of an inch, that's what we have to have. And we have a 2 inch wide floor joist. And if we can get into the center of that, we're going to have a full 1 inch. And if you were to do a bunch of fancy calculations, you would discover that you're getting actually more than 400 pounds per lag screw. You're probably getting 450 or 500. So it's really important to get into the center of that floor joist. Now we also need to worry about something else, and that is the connection between the upper top plate and the lower top plate. This connection, or this face, this interface right here, is called an unsecured shear plane unless we do something about it, and it's a stress point. So we need to attach this and this together. Now we do it the exact same way. We use 12D commons, that's a type of nail, and those can resist 188 pounds each. We divide 188 into our 8,700 pounds of resistance of our shear wall. And when we do that, we end up with 46 nails. So along our 10-foot shear wall, we're going to need 46 nails. So as of now, we understand that we're going to need 46 nails, 21 SDS screws, and our connection to the floor, our shear wall to the floor will be complete, and we did not have to tear out the ceiling. That's what's important, and that's what saves all the money.
Audio Jungle.
So I hope you found this video helpful. I think it'll save you a lot of money, certainly a lot of grief. So when you're interviewing your contractors, the things that you first want to talk to them about is how are you going to connect the shear walls to the floor? If they're not going to do anything at all, well, you should probably talk to somebody else. If they want to tear out the ceiling to do it, well, you need to ask them, are you going to patch it up so it looks just like it's supposed to, before you did anything? If they can do that, well, then they're worth, considering. And then, of course, if they understand to go ahead and use these lag bolts like this to connect the shear wall to the floor, that will be by far the least misery overall. The cost, they might charge you more, and you have to consider, well, should I go ahead and pay the extra to get the ceiling patched, for the sheetrock or plaster? Or should I go ahead and pay more and just make sure I don't have to deal with it at all? So those are some options for you when you're interviewing your contractors. Those are some questions you might want to consider. Now, if this video was helpful, please let me know. And I'm also I'm just sitting in my office. This is a totally homemade deal. I have nothing fancy going on here, and I have no idea if there's anything that I missed in my videos. I should have made something clearer. I forgot something. There was a part where I couldn't hear the audio, all sorts of things. I do hear back from people, and it's very, very helpful when I hear back. So anyway, I hope this video was helpful, and I hope to see you again.